Bismillahirrahmanirrahim. Let's start our new topic for heat and mass transfer, which is that of the fins. So till now we have gone over the thermal networks topic or topics in which we discussed various types of resistances, and now we are going to start the heat transfer using fins, which is also called extended surface heat transfer. Extended surface heat transfer. So what is being shown over here is, it is figure 3.13 of our book, and A refers to bare surface, whereas figure B refers to a finned surface. So this is a bare surface without the fins, and B is in fact the surface where the fins have been put on. So you can readily realize that by putting the fins on, what we do is that we try to increase the area of the heat transfer. We increase the area of heat transfer, and that increase in the heat transfer area would result in more convection heat transfer along with radiation heat transfer. But over here we would be dealing in convection only, which of course results in more or large amount of heat transfers. Now this is the case. In this figure we are being shown that see, there is an original assembly, and on that original assembly the fins are put on. So the point where the fin starts from is called the fin base. The point where the fin starts from is called the fin base. And the place or the point where the fin ends at is called the fin tip. So, and you would realize that if this surface, if the original surface is at, for example, 300 degrees Celsius, so the temperature at the fin base would also be 300 degrees Celsius, and the heat will be conducted from the original assembly into the fin via the fin base. The energy heat would be conducted into the fin from the original assembly into the fin via fin base. And while the heat is flowing in this direction, there are two things that are taking place. One, the heat is being conducted in this direction along the length of the fin, and at the same time the heat is being lost away via convection to the surrounding air or the surrounding fluid. So when the heat reaches the fin tip, so at the fin tip there would not be any conduction further, because that is the point where the fin ends at. So from the fin tip it would only be convection that will take place. The temperature would be maximum at the fin base and it would be minimum at fin tip. The temperature in this case that we are discussing, so the temperature would be maximum over here at the fin base, and as the heat flows along the length of the fin, its temperature would continuously decline. So at all those sections, the temperature of the fin will continuously decrease, and it would be minimum at the fin tip. Now, what can be the minimum temperature at the tip of the fin? See, the minimum temperature at the fin tip can be, it may not always be, but the minimum temperature can reach to as low as T infinity, where T infinity is the temperature of the surrounding fluid such as air. Of course it will not go beyond T infinity, it will not go below T infinity, Otherwise, instead of losing heat, it will start gaining heat. And it is not always necessary that at the fin tip we have the temperature the same as T infinity. It may be greater than that, right? But the minimum temperature that we can have at the fin tip is T infinity and not any lower than that. So this is the original assembly on which we have placed this fin, and you can see that now this area, which is evident from this box, that area on which the fin has been put on, so that small area has been replaced by this large surface area of the complete fin. So the enhancement in heat transfer results due to the enhancement in the fin area. So the heat will continuously be conducted, and at the same time it would be convected, and from the fin tip it will be lost via convection only. It will be transferred via convection only. This is the base of the fin, and this is the tip of the fin. Now there are some examples of fins. As we can see over here, that as the liquid flows through those tubes, so as it flows through the tubes, so we can see those circular fins. So those orangish components are in fact the circular fins which are placed on those cylindrical tubes, and you can see that a small surface area has been replaced by a large surface area, which will result in larger amounts of heat transfer. Similarly, these are the channels through which some liquid is flowing, and if we put those channels in those fins, or if we put those fins around those channels, of course that will increase the heat transfer area. There are some other examples. For example, this is the back of the refrigerator, which is the condenser. So this is these are the condenser pipes through which the fluid flows, and all those things, those longitudinal pipes are in fact the fins that are placed on original pipes, and of course they result in their purpose is to increase the heat transfer. Similarly, over here we are being shown the same things. There are pipes, and those pipes have got those plate type fins, and that will certainly increase the heat transfer area and subsequently increasing the heat transfer rate. Refrigerator is one example. You would have seen the fins on the engines, on internal combustion engines, for example. And over here, I mean, it can be condenser, it can be evaporator. So hot water comes in, and we want the cold water out of it. So the cold air flows over those pipes, and those pipes are, the heat transfer in those pipes are being supplemented by those fins. For example, you can see those fins on the evaporator section of air conditioner, section of the air conditioner, which is the inner unit. So those fins means those enhanced heat transfer areas will increase the heat transfer rate between the hot fluid and the cold fluid. These are some configurations, that is figure 3-15 of our book in Cropper and David, and the fin may be straight as shown in figure A of uniform cross section. Similarly, in B it is non-uniform cross section. In figure C it is annular fin, just like we were looking at one of the examples of annular fin in previous slides. and this type of fin is called pin fin. So there are various different configurations: uniform, non-uniform, triangular, annular, pin, etc., etc. Now starting with the fin energy balance, we will see in a bit where will this fin energy balance will lead us to. Or let me tell you over here that what we are going to do, we are going to determine the we are going to find out the temperature distribution in a fin. Means if this is the fin, so how will temperature vary all along the length of the fin, all along the length of the fin. So if this is the fin, then how the temperature would vary all along the length of the fin. So we are trying to find out temperature as a function of x in case of fin, and heat transfer rate we will see with the course of this PowerPoint presentation. So over here is taken a differential element in which Q is coming in, is being conducted in, and the heat which goes out of this differential element is Qx plus dx. So Q which is coming in will be utilized in two ways. One part of it will be conducted further, or it will leave the differential element, whereas another part of it will be transferred to the surrounding fluid via convection. And the same thing is being shown over here. If Qx is the amount of heat energy which is coming in, so it will be utilized in two ways. One part of it will be transferred, will be conducted further, and one part of it will be convected to the surrounding fluid. So this is the simple energy balance that we are talking about. Now as just discussed on the previous page, Qx will be Qx plus dx plus Q convected. See, we are calling Q convected as dQ convected. The reason is that this surface area will be differential, will be infinitesimally small, whereas this cross section area through which heat is being conducted in is finite. It is not infinitesimally small. You can see over here that this cross section area would have a certain finite value, but since the length of this element is very small, it is dx, so therefore the surface area would be infinitesimally small, it would be differential quantity. So that is why with convection heat transfer we have written this d sign, whereas with conductive heat transfer which is coming in and leaving this element, there would not be a d, because that area is in fact finite. Cross sectional area is finite. So Qx would be minus Ka dt by dx, where A would be the cross sectional area, and Qx plus dx is this quantity. We have seen this thing before in chapter number 2 while we were deriving the heat diffusion equation, that Qx plus dx is equal to Qx, means whatever is coming in plus change in Q with respect to x times the total length, means dx. So Qx remains Qx, and it is d by dx of Qx. So d by dx of Qx, and Qx is minus Ka dt by dx, and it is being multiplied by dx, so therefore it is being multiplied by dx. Now minus will come out of the differential sign, K and cross sectional area may also be taken out of the differential sign, and it would be second differential of temperature with x, second differential of temperature with x times dx. And the heat transferred via convection would be HA times T minus T infinity, where area would be DAS, would be the infinitesimally small area as is being shown over here. Now if you put 2 and 3 in 1, Qx remains Qx, Qx plus dx can be written in this form as in equation 2, and the heat transferred via convection may be written in this form as expressed in equation 3. So then Qx will get cancelled out and we will be left with these two terms only. Kac, second derivative of temperature with x times dx, and this minus would become this plus sign would become minus h times infinitesimally small area times t minus t infinity as 0. Now if we divide throughout by Kac and dx as well, so the first term would only be second derivative of temperature with x, and it would be h ds over Kac dx times t minus t infinity as 0. Now if we separate out das over dx, if we separate out das over dx, so that can be written as perimeter. That can be written as perimeter. See, das can be written as p times dx. You should be able to realize that this area das is equal to this whole perimeter times dx times the length. So therefore das is equal to p times dx. So therefore das upon dx is equal to perimeter p. The rest of the things remain the same. So therefore second derivative of temperature with x minus hp over kc times t minus t infinity becomes 0. Now if we now define this t minus t infinity as theta at any x, so it means that theta at any x is equal to temperature at that x minus t infinity, which means that theta at base would be the temperature at the base minus t infinity. If you are talking about the base of the fin, so theta over here would be equal to temperature at this base minus t infinity, whatever is t infinity. Similarly, theta at the tip would be equal to temperature at the tip minus t infinity. So theta at any location, be it tip or base or any other location, so theta would be equal to temperature, theta at that location would be equal to temperature at that location minus t infinity. Of course, you may realize that theta at base would be having a higher value because temperature at the base would be higher than the temperature at the tip, if we consider the example that we were discussing a while ago. And in that case, theta at tip would be equal to a small quantity because temperature at the tip would be a small quantity. And if the temperature at the tip approaches t infinity, if it becomes same as t infinity, so then theta may also be 0. But as I explained to you previously, that temperature at the tip of the fin may not always be equal to t infinity. It is a minimum value of temperature that it may have, or it may be greater than t infinity. This is not unusual, this is very common. So if we say that t minus t infinity is theta, and we say that this hp over kc is m square, where m is not mass, m is only a quantity, and we are calling this hp over kc as m square. We are doing that for a very particular reason we will see in a moment. So then equation 4 would become that hp over kc would be written as m square, and this t minus t infinity will be written as theta. So it has been written as theta. And over here you may see that second derivative of temperature with x has been written as second derivative of theta with x. See, over here we have not replaced this temperature with theta. We have not replaced this temperature with theta. Why? Because theta is not equal to temperature. Theta is in fact temperature minus T infinity. It is the difference between these two. So if theta is t minus t infinity, what would be the first derivative? D theta by dx would be dt by dx minus 0, because t infinity is constant quantity. T varies with x. Of course, temperature at the base would have some other value, and the temperature at the tip would have some other value. So it means temperature is varying with x. But is T infinity varying? No. Temperature of the surrounding air would remain the same. So therefore T infinity, differential of T infinity would be 0, because T infinity is constant. So theta is T at x minus T infinity, but d theta by dx would be equal to dt by dx, and if the first differential is the same, then the second differential will also be the same. So therefore we are writing second derivative of theta with respect to x in place of second derivative of temperature with respect to x. We are not simply writing this theta in place of this t. And now this is the second order differential equation, the solution to which probably you would have gone over it in second year of your undergraduate degree program, is given as c1 e to the power mx plus c2 e to the power minus mx. That is why we were writing it in this particular form. Over here the point is that you do not need to remember how did we solve it to this point. All is required is that you just recall that the solution of this second order partial differential equation was this thing, c1 e to the power mx plus c2 e to the power minus mx. Now if you take a look at this equation A, we are calling it A. What is this A? C1 is a constant quantity, E is a constant quantity 2.71828, M is a constant quantity as well, CH is constant, perimeter is constant, K is constant, cross sectional area is constant. So all those are constant quantities. So what equation A is about? It is about the dependency or the relation between theta and x. Now out of theta we have got t and t infinity, and out of these two t infinity is constant. So in fact equation A is talking about the relation between temperature and x. Means this equation A is simply the temperature distribution equation. Equation A is very simply the temperature distribution, means how would temperature vary along the x-axis, along the length of the fin in x direction. So what we need to do over here is that we need to find out those two unknowns C1 and C2, right? And if you recall, we have done the same thing in the thermal networks case, where we had a t as a function of x, and then we had the two unknowns C1 and C2 in case of plane wall, in case of cylindrical coordinate system. Those were the two cases which I had solved, and then I had left the third one for you which was a spherical coordinate system. And then we used to find out the values of C1 and C2 by applying the two boundary conditions. So we will do the same thing over here. We would be requiring two boundary conditions, and we will be putting those two boundary conditions in equation A to find out values of C1 and C2. And once we find out C1 and C2, we will put them back in A to get temperature as a function of x. Means we would be able to find out temperature distribution in case of fins. Means how does the temperature vary along the length of the fin. But before we start applying the boundary conditions, we would be dealing with three fin cases. And what are those three fin cases? This is very important point that you need to understand very carefully. The first case is the general case. General case means this is the fin attached to some original assembly. The heat will be conducted into the fin, and as the heat is conducted all along the length of the fin, the temperature would keep on decreasing, and it would be minimum at the tip of the fin. So while it is being conducted further, it is the energy is also being convected to the surrounding fluid, and from the tip of the fin the heat will be transferred via convection. So Q tip is equal to Q convected. This is the general case. Means this is the case of the working of the fin. Whereas in case B, the case B pertains to insulated tip case. Means it seems as if we have insulated the tip, so therefore there would not be any heat transfer from the tip. See, over here we do not insulate the tip because that is against the purpose of using the fin. See, what was the objective of using the fin? The objective of using the fin was to increase the heat transfer rate. If we want the heat to be lost from the original assembly into the surrounding air. So if we insulate the tip, the heat transfer from the tip of the fin will not take place. So that is against the objective of putting the fin. So in insulated tip case, we do not insulate the tip of the fin. Rather, insulated tip means that the area of the fin, surface area of the fin is very large. The surface area of the fin is very large. So large that the area of the tip of the fin is very small in comparison with the rest of the surface area of the fin. The surface area of the fin is very large. So large that the surface area of the tip of the fin only is very small as compared to the surface area of the rest of the fin. And therefore, the heat transfer that will take place from the tip of the fin would be negligibly small when it is compared with the convective heat transfer taking place from the rest of the fin. The convective heat transfer taking place from the tip of the fin is very small, so small that it can be neglected when it is compared with the convective heat transfer taking place from the rest of the fin area. So this is what is meant by insulated tip. We do not insulate the tip, we are only saying that the area of the fin tip is very small, so small that the heat transfer taking place from the fin tip is negligible as compared to the heat transfer taking place from the rest of the fin, and therefore Q tip is 0. Therefore the heat transfer from the tip of the fin is 0. We do not put the insulation on. What does it do? It reduces the large expressions that we will come across in case A. This assumption of insulated tip case will reduce the large expressions of case A into half. So this is the simplicity that we get as a result of assuming the insulated tip. And the third case is that of the long fin case. See, how long can the fin be? We can increase the length of the fin, and as we increase the length of the fin, the temperature along the length of the fin will keep on decreasing, right? Will keep on decreasing. And how far it can be decreased? It cannot be taken below T infinity. So there will come a length of the fin where the temperature at the tip would approach T infinity, and then theta would become 0. So long fin case means the length of the fin is so long that the temperature at the tip of the fin approaches T infinity. This is what is meant by long fin case. Of course, it is not possible to have long fin case all the time. For example, let me give you a very simple example. You would have noticed that there are fins on the motorcycle engine, right? And if you touch those fins, you feel that the temperature at the tip of the fins is a little bit higher. It is not comfortable to touch those fins. Means the temperature at the tip of the fin is not equal to T infinity. It is having some higher value such as probably 50 or 60 or any other higher value depending upon the heat rates. So it means that fin is not long. That case is not the long fin case. So if we try to make the fin long enough so that the temperature at the tip of the fin approaches T infinity, becomes almost T infinity, so what will happen is that the length of that fin would be too long. The length of, let me show you. So the length of this fin would be very long, right? And if you make it long, for example, if you make it 1 foot long or 2 feet long, so where would the person who is riding this motorcycle would keep his feet? See, so there is a space constraint now. So due to some space constraints or some other constraints, it is not possible to have the long fin case all the time. It is not possible that at the temperature at the tip of the fin we have the temperature at the tip of the fin approach T infinity. And secondly, even if you make it a 2 foot long fin, so you will realize readily that it will have, see, if you make this fin 2 foot long in the case of motorcycle, so the larger the length of this fin is, it will put more and more stresses over here. It will put more and more stresses on the base. So stress constraint is one constraint, space constraint is one constraint, and there are some other constraints as well, due to which we may not have temperature at the tip approach T infinity all the time. So these are the 3 fin cases that we would be dealing with. Now, what are the boundary conditions? So what we will do is that we will be having different boundary conditions for all the 3 fin cases, and therefore we would have different temperature distributions for the 3 fin cases. So let's take the first one. In the first one, which is the general case, these are the 2 boundary conditions. What is the first boundary condition? The first boundary condition is at the fin base, and it says that theta is equal to theta b. Means what we are saying is that we know temperature at the base of the fin, which is T base, which is T base. So if we know T base, so therefore theta at the base would be equal to temperature at the base minus T infinity. So the first boundary condition is at the base of the fin, whereas the second boundary condition is now at the tip of the fin. And this will be the same in all the 3 cases. Means one boundary condition in all the 3 cases would be at the base, and the second boundary condition in all the 3 cases would be at the tip of the fin. Now the second boundary condition is what the general case is about. Is the second boundary condition. So what the general case is about? When the heat reaches via conduction till the fin tip, it is then further transferred via convection. It is then further transferred via convection to the surrounding fluid, and this is the boundary condition number 2, that the heat conducted till the tip of the fin will be convected away to the surrounding fluid via convection, will be transferred via convection to the surrounding fluid. Now the heat that will be conducted till the fin tip will be written as per Fourier's law of heat conduction, means minus Ka dt by dx at x is equal to L. This is the point where x is 0, fin base, and this is the point where x is equal to L, fin tip. So minus Ka dt by dx at x is equal to L. This heat which has reached L, which has reached the fin tip, will be further transferred via convection, means HA delta T. So H times this fin tip area, which would be the same as cross sectional area in this case, times temperature at the fin tip, temperature at x equal to L, whatever that temperature is. Of course that would be different from T base, that will not be T base, minus T infinity. So as just discussed, this area, those two areas would get cancelled out because they are the same. The cross section area is the same as the fin tip area. So therefore they will get cancelled out, and we will have minus k times, see, dt by dx can be written as d theta by dx. Again we are not writing t as theta, but we are writing dt by dx as d theta by dx as explained previously on the previous slide. So this dt by dx may be written as d theta by dx at x equal to L, and on the right hand side we will have h, and this t minus t infinity may be written as theta at the tip at x equal to L. It is not theta into L, rather it is theta at x equal to L. Now for the second case, case B, insulated tip case, the first boundary condition remains the same, means we know the temperature at the base of the fin. So therefore at x equal to 0, theta would be equal to theta b, which would be Tb minus T infinity. However, the second boundary condition is again the same what the insulated tip case is about. What it is about? The heat that is conducted till the tip of the fin will not be further convected away, because rather it is being neglected, because the area is very small as compared to the rest of the fin. Therefore the heat conducted till the fin tip would be 0, will not be further transferred. It is negligibly small, it is approximately 0. So therefore minus k dt by dx at x equal to L, the same thing that we had in the first case, will be 0. It means that dt by ds can be written as d theta by dx, so d theta by dx becomes 0. d theta by dx becomes 0. And in the third case, which is that of the long fin case, again the first boundary condition remains the same. So in all the three cases the first boundary condition remains the same, it is only the second boundary condition which changes. So the second boundary condition says that at fin tip, theta approaches 0 at x becomes very large. See, when the fin becomes very large, of course it will not become infinity. Infinity over here is an indication that the length of the fin would be large. So as x becomes very large, theta would approach 0, because at x becomes very large, the temperature at the tip would reach T infinity, and therefore theta would approach 0. So these are the two boundary conditions in all the three cases. Now we will apply those two boundary conditions for each of the cases to find out C1 and C2, and then after finding out C1 and C2, which would be different for all the three cases, we will be finding out the temperature distribution in all the three cases, which would be different, which would be having different expressions, but we will go over how to remember those expressions. It is not that difficult that it looks, right? At the end you will find out the things very easy.